Hello, anchoring phenomenon students. This is the first of two videos that I want to share with you. This one, I want to talk a little bit about the science behind the burning of the steel wool. We didn't really dive down into that and get any satisfying answers. So I want to take a few minutes to look at that and to show you what we did in class eventually after several weeks of thinking about all kinds of chemistry to finally address what was going on with the steel wool. The second video will be about sort of pedagogical choices and sort of a unit plan to give you a sense of what that might look like. So let's get underway here. After quite a bit of time of exploring a lot of different things, and you'll see in the pedagogy video, you'll see lots and lots of activities. We finally got around to thinking about steel wool itself. So what I shared with the students was this, that steel wool is really mostly iron and a little bit of carbon, and some of you may notice some black soot coming out of the burning process, and and that was likely to be carbon. And it says here no hydrogen and no oxygen, and that's important because the students have learned at this point a combustion reaction which depends upon some sort of hydrocarbon and oxygen coming together to create CO2 and water and energy. But since there's no hydrogen involved and no oxygen in the steel wool, it seems unlikely that this can be a combustion process. I also share with them the wooliness of it helps to move the heat along the thin strands. So the temperature of the individual strands can change very rapidly, and the heat can be conducted along the strands, and that turns out to be a key element of the whole process. We wouldn't be able to do this with big, thick slabs of steel. After discussing that a little bit with students, they have this as sort of a warm-up problem, prompt getting them to think about the idea that iron will oxidize, and in fact they bring that up quite a bit. They think it's rusting, and in a way it is. It's a rapid rusting that happens. And you can see here a reference to 5 types of chemical reactions, which is some back knowledge they have by this time in the unit. And I asked them to propose some way in which the rusting of iron could happen over a long period of time, and to try to determine what kind of reaction that is. And then I asked them to try to think about the differences and similarities between the rapid oxidation process that we saw and the slow rusting process that they know happens out in the world. So they do this in little groups, and then we have conversations about it, and we sort of fill this in at the board. And here's a sort of typical conversation. The steel wool is 98% iron, so that's the source of the iron. The oxygen, they can tell you, will come from the air, and this will combine into some kind of chemical reaction to some sort of iron oxide. And again, I had asked them not to worry about balancing, even though this looks balanced right now, but there are some other considerations we need to think about. They correctly identify this as a synthesis reaction, and they want, and it's a combination of elements. So that's a sort of satisfying idea that you've got this iron sitting on the pan to begin with. Oxygen comes from elsewhere, and then this is now the new material that's sitting on the scale, and it clearly has to weigh more than just the iron by itself. There's still more to think about here, a lot more, but this is an important piece. Extending this to sort of what makes it happen quickly, they can call upon their thinking of the way in which a hydrocarbon like butane, which is in the little lighters, can burn in the presence of oxygen, producing water, CO2, and energy. This is a really specific kind of chemical reaction called combustion, and that energy is supplied to this bonding process over here with the iron and the oxygen. So this is a proposal on their part that maybe that happens, and ultimately, I'm going to skip quite a few steps here, but ultimately that energy gets both the iron and the oxygen moving very quickly. In the case of the iron, vibrating quite a bit, and in the case of the oxygen, moving pretty rapidly. And so the collisions between these two things happen much more frequently and much more energetically, and allow for the bonding here to happen. So this is really eventually a pretty complete discussion of how this all plays out. Collision ideas and energetics of collisions and so forth. It's pretty interesting stuff. You can also see that oxygen plays two roles. Some of the oxygen from the air is being added to the iron to create this iron oxide, and some of the oxygen from the air is being used to ignite the butane and create the products of combustion. So there's a lot going on here. One more additional aspect about this that can show you how much chemistry we did during this unit is for us to look back at the periodic table. For a long time, we only dealt with the first two columns, and then columns 3 through 8 shown here, and chemical reactions between those parts. And we were ignoring the vast middle ground here because there's really tricky stuff in the middle, and the pieces in the middle don't have as simple a construction as the outer edges do. Iron is in this set of transition metals, and the twist, which I revealed to them here, is that they can have a variety of valence electrons. And in fact, two prominent modes for iron is that it either has 2 electrons to donate or 3. And that is a really interesting possibility, which allows me as a teacher to kind of push my students to do a little bit of sort of computational thinking and computational argumentation. So we'll take a look at that in a sec. So here's kind of a busy page of work that we did at this point. I asked the students to make the assumption that iron has 3 valence electrons, and they went ahead and examined then the synthesis of iron and oxygen. They balanced an equation, and then they used molar ratios to demonstrate conservation of mass. So there's some mathematical thinking there, and then they can show a percent increase if this is the mode. If this is the mode here, 4 irons and 3 oxygens combining to make 2 iron oxide molecules of this form, then we should be able to show that that when you burn it, when you synthesize that iron oxide, you should get a 43% increase in mass. That can be compared with a similar observation that if you make the assumption that iron has just 2 valence electrons to donate, you can go through a similar process and show that you'll only get something like a 25 or 28% increase. And that sets up the following task. Let's see if I can find it here. If we just take a look, we summarize here mode number 1, the donation of 2 electrons, mode number 2, the donation of 3 electrons. And we should be able to look at this, come up with a prediction for how much of a percent increase in mass each of these reactions should command, and then we can one last time rerun our process. So we go back to the burning steel wool, do it again, get some really carefully viewed data, try to approximate how much of the steel wool actually burned, and then the students are set up with their own data, and the task, which is to write a claim based on evidence and reasoning that either this mode or that mode dominates the process. So really deep, rich assessment that can be done at the end as a very big summative assessment that includes chemical reactions, some little bit of stoichiometry, and and lots of thinking about the way in which iron and oxygen might bond. So we eventually get there. This was a several week unit with lots and lots of material between the beginning and the end, but we came back to the steel wool at the end to use it as a way to do sort of a final assessment of much of what we had learned in that time.